It's for me a pleasure to welcome Dr. Neil Hausmann to our symposium. He started in 2004 in the Pioneers breeding platform for drought tolerance in maize, and currently, as field sensing leader, he develops cutting-edge field sensing techniques for improved prediction accuracy in diverse agricultural systems. So please join me in welcoming Dr. Neil Hausmann.
Good check. Okay, great. So I'm here. I'm representing another facet of diversity. So to Wolfgang's talk, I'm representing a industry perspective here, and I think hopefully it will tie in with a lot of the other discussions. And I'll also start out here tying in about a little bit to my my evolution as a Pioneer employee. And so, in some ways, I think ties into where I feel breeding needs to go, which is more or less the subject of my talk here. But so I started, as Rodrigo said, I started very focused in a drought breeding program. I was hired straight out of grad school at University of California, Berkeley for my, I did kind of QTL analysis, looking at QTL by E interaction. So I was very focused. Pretty much, I got the only job that I was qualified for, so I was very thankful for that. And I happened to get a very well-paying job, so that's why I've stayed for 15 years. But very focused, measuring physiological traits for drought breeding. And drought is very complex, very hard to breed for. Huge changes in environment, changes from soil, from plot to plot, very different quantitative genetics, many quantitative traits. And so we were forced very early to look at high-throughput phenotyping solutions for measuring some of these very complex traits. Understanding the environment, so lots of in-field sensors. We used manned aircraft as well as satellite imaging to try to understand field variability, which was huge. And so a lot of the aspects that I'll be discussing as we move to kind of broader level issues were front and center when I was doing maize breeding. I then moved, so with all that phenotyping, that we were still at that point in 2004, as I kind of see it as the age of genotyping, when all of the genotyping technologies, sequencing technologies, we were moving from kind of small scale genotyping to huge industrial scale genotyping. And phenotyping at that point was still kind of an amateur sport. My career is mostly seeing that evolve from something that only physiologists might want to do in their spare time to now a huge focus for our breeding efforts. Because, of course, it is a lot of the mega trends in agriculture. There's fewer workers. We're working, working with more complex systems. With the rise of digital agriculture, with tons of ag tech startups working to provide digital solutions for farmers, there's an increased need for measuring crops, understanding what the crops are doing, and also predicting what the crops are going to do. And so, finally, to tie in, I think, with some of Wolfgang's final comments as well, our focus here for prediction is very much focused on what types of predictions and what accuracy of predictions can add value now. So, of course, we could try to predict, and we will, that's maybe the 200-year piece, try to predict what exactly is the yield of a specific genotype in a specific field at any point in the future, and that is a very, very tall order. But if we can just say, predict this genotype is going to outperform this genotype across the range of environments we're looking at, that has a huge benefit for breeding organizations. So we're kind of start small with our predictive abilities and hopefully build on that. And I also really love this figure, which is drawn by David Bowen, one of my colleagues, really emphasizing throughout here all the different types of input data that we'll need to drive accurate predictions. Because of course predictions are driven through the inputs and the model itself, and my life has been about building these inputs at scale, so I'll be discussing that as well. So some small, I'll discuss a little bit of work in satellites, a lot of our work in drones, and then a few other pieces in terms of measurements of the environment. So this is just for context, Corteva, like many, like actually probably all of the other seed and chemical input companies, is building a digital platform. And we see this as a key aspect of our competitive, staying competitive in the future, is not just adding value through the inputs, through better quality seeds, better quality crop protection chemicals, but also integrating those into a system that makes farmers' lives easier, simpler, and more profitable. And so we, at the same time that Dow and DuPont merged, about a year ago, we also purchased Granular, which was a startup in San Francisco. We purchased them for $300 million, and we built it mostly on this. It was a leading farm management system. So farmers were able to load in data about their operations and simplify their operations. It really wasn't all about agronomy or telling farmers what to plant, where to plant, how to grow their crops. That was the part that we had been building internally with this Encirca platform. So Encirca, kind of like Climate Core, was very focused on more about the input piece. And so one of the major aspects is planting densities as well as nitrogen for nitrogen. And then acre value was another piece built with Granular, looking at price of land. But ultimately, the idea here was, how do we bring together systems that help farmers with the business side of their operations, and then systems that are associated with optimizing their agronomy. And ultimately, the goal for a lot of what else I'm talking about, the seeds, crop protection, and digital solutions often will come together through this platform. So just for context. And so this is describing a bit of what I'd say we built over the past maybe 20 years, especially within heritage, within the kind of DuPont pioneer pieces. But we built a huge, very efficient, very effective genotyping engine, where we were able to categorize the genotypic variation at huge scale, and understand relationships through the pedigree, and at the haplotype level. And so that level of genotyping, understanding our germplasm is really key and an core aspect of the modern breeding program. And then we did a lot of, this is kind of where I had more of my life, lots of work on phenotyping, both from experimental analysis, experimental design, analysis perspective, but also in setting up managed environments where we can control drought very, very precisely, and that, by controlling the environment, we get much better separation of genotypes and much better ability to then select genotypes in those environments. This standability piece, we also developed big machines that simulate high wind conditions. Once again, to try to control the inputs, the input information, to have a very, very tight ability to separate out genotypes. Now, what I'll point out in this picture is kind of what we're doing. This is very much a plus situation. We had a really strong genotyping, really strong phenotyping. What tied it together is whole genome prediction, or kind of our genome-wide prediction engine. But that, as is kind of, I think, now the norm across industry, very much marker trait association and then selection on a per trait basis, right? So our selection indices are linear selection matrices, or linear selection equations. Most of the time, I'm going to put this relative weight on yield, this relative weight on moisture, this relative weight on northern leaf blight resistance. Based on the weighting, I'll come up with some linear equation that then I'll use. And one of the problems with that, of course, is that, as anyone who has any basics of physiology knows, there's a huge interaction between traits, not just at the genetic level, but at the physiological level, such that, for example, higher ear height and higher yields for corn often lead to greater stalk lodging probabilities. So you can't really have, the relationships are not linear. So our model at that point underperforms and does not kind of meet our needs. And so one of the major investments we've made over the past 20 years has also been in building up a crop growth modeling competency. And so this was actually done primarily in conjunction with university collaborations. A large part with University of Queensland in Australia, who built the Absent platform. That we kind of built this with, or built this in conjunction with them. University of Wageningen as well. So there's a large part of kind of industry and academic collaboration as part of this, and that continues to this day. Then we built up, and this is what I was actually hired for, a huge kind of a phenotyping effort to measure these traits, the genetic parameters that go into our model. Because of course, with Absent, we started with a non-genetic model. It's a generic corn model, or generic wheat, or generic sorghum, but doesn't necessarily have kind of the parameters associated with elite new genetics, nor any parameters that separate out genotypes. And so that's what we built, but we had to measure all those different parameters. For example, the size of the length and width of the biggest leaf. So then we had to build out the equations in the model, but also methods to measure that longest leaf at scale. And as you can imagine, most of that is just like you guys do in your graduate studies, a lot of measuring tapes. Very, very resource intensive, very hard, a lot of error in those measurements as well, because at 3 in the afternoon, you're tired, you're hot, you don't really care what that leaf looks like. You just want a number to come out and you want to move on to the next play. And so and I'm speaking from the pure experience, so there's no, but that's life. That's the way we need to do things. One of my current obsessions, and you'll see through the rest of the talk, is focus on measuring these things with less human intervention. And then there's a huge aspect of understanding the environment and management aspects of that as well. So getting high throughput information around soils, around weather, getting machine data to understand planting rates, chemical applications as well, loading into the model, and then you get this output. So these are simulation outputs of different genetics. This is one of our hybrids that we are selling now. But then we use these simulations as part of our advancement, our decision making, whether we actually should sell this new hybrid or this new hybrid based on simulated outcomes in the United States, for example. And so these pre-commercial, this is actually from 2012, so still kind of building upon this. But really, this is all based around this crop growth and development model. So very, very simply taking in the inputs, understanding of the processes of crop growth and development, and then distilling those processes into equations. And then lots of these, let me see. Some of these parameters then are set as genotypic parameters, which then each genotype would have a different value for that. And then we need to measure that. Other ones are fixed across all genotypes, but we need to understand which have genetic variants and then which ones have an importance, kind of from a sensitivity analysis, which ones have importance in separating yield. But we built this out and distilled it into a crop growth model framework that we can use. The next phase in the evolution is connecting the two parts. So we have this whole genome prediction-based method where we've done per trait, marker trait association. We have this platform that connects the traits together, connects to the environment, and then through pioneering work with huge contribution from Frank Tempno, who was a graduate of this university, connected the crop growth model with whole genome prediction. Adding the Bayesian framework that we use for whole genome prediction and connecting that to some of the parameters in the model. So we can look at the genes that underlie the traits and then how the traits interact with each other and with the environment and get a kind of holistic view on how different traits will impact yield, how different traits will impact each other, how those are responsible in the environment, and then what's the genetic underpinning of those traits. And this doesn't need to stop per se at the marker level. It can also include models associated with gene networks and associated with kind of more at the base physiological level as well. And so the framework is very extensible as well. So this is from one of the papers. Just showing a little bit of what this whole crop growth model whole genome prediction tie-in looks like. And so this is the case where the model was trained under water-limited conditions, or the whole genome prediction was, the estimation set was developed under water-limited conditions, and then that's what Bayes A is, and then we're looking at the crop growth model whole genome prediction versus the standard whole genome prediction. And this is then the correlation with the observed yield. And so you can see in both of these cases, this is trained in year 1 and predicted in year 2, or trained in year 1 and predicted in year 1. And you can see in both cases, the CGMWP and the whole genome prediction are pretty similar and positive. And you can see this in these relationships as well. So equal, there's not much value in this case of going through the trouble of connecting to the crop growth. The real value comes in this situation. The estimation set is from non-water limited conditions, and we're predicting it to water limited conditions. And so in this case, you can see actually kind of the worst case scenario with just the whole genome prediction, we actually get a negative correlation, which means any genotype you select, if you select it as the best using whole genome prediction, it will be the worst yielding, or could be the worst yielding. And so it's a huge watch out. And I mean, this is also well known in estimation set design. You need to choose the right environments so that you're interpolating, not extrapolating. So it's not an unknown problem, but it's not handled in the whole genome prediction framework. But with the crop growth model, because it has this explicit tie-in between traits and environment, we can handle it, and you end up with a positive relationship, which means that it has predictive power and can be used should be used for selection. If the case, and this does happen, you're using just whole genome prediction, you can really be sunk. And so just to call out, this is published, it's relatively academic in nature. It's kind of framed to be significant, but still it does show the value of connecting trait to trait and trait to environment in your predictive framework. And so then, as I said, and none of these pictures are ours, but they're just for, and nor do they serve as endorsements, but just to give the idea, in order to make this framework work, you need to be able to measure these physiological traits at scale for all of our genotypes, for all of our breeding programs, which is, of course, covering tens of thousands, hundreds of thousands of plots worldwide, and so you need scalable systems. Satellite imagery, of course, is privatized now. Higher resolution, higher speed, lower cost. There's huge advances in the kind of the miniaturization and privatization of satellite imagery. So big props to our government funding agencies and then the entrepreneurs who took that big. The scale up of drones as an imaging source. Once again, I have to call out now the defense industry, but definitely starting 5 years ago in this space, really taking advantage of advancements in miniaturization of sensors and control systems, automation here, but that's been a huge plus and a huge, I think, advance for breeding. And then this age is coming. There's a lot of new companies in this space, still trying to figure out value, but in terms of ground-based imaging, and is in-canopy imaging and what the value is going to be there. I'll describe especially what we've done in the drone space. A drink. So that was a well-timed sip of water for you guys to read my slide so that you can follow along. But really the issue here, both for our breeding traits, but also for these modeling traits, field phenotyping is still highly subjective and slow and costly. And that's a huge challenge for scaling breeding programs and building predictive models. And so really we need systems to measure phenotypes at scale, bring in management and machine data, and then better understand the environment, but all using new technology and techniques to build the golden stack. And this is just an illustration of kind of, I think, where we're going now. This is an example of an in-field sensor, a drone, and satellite imagery, and the value and the opportunities here. So of course, with in-field sensors, installed sensors, very, very small spatial coverage. Making one measurement per hectare is probably already very expensive and very generous. but you can make huge numbers of measurements per season. Even you can make measurements at a 15-second scale all through the season. So you have huge temporal resolution and very poor spatial resolution. With a drone, you get the opposite. You can have good temporal resolution, maybe 3 to 6 measurements per season, still expensive and difficult, but you can measure 3 million data points per hectare. You can measure huge, very, very high resolution, and if you're able to go from picture to trait, a lot of value there. And then with satellites, as I said, scalable, cheap, no investment necessarily needed from our side, high coverage based on the privatization, but big pixel sizes. So the pixels are much bigger than any plant that we grow, and so there needs to be then, what is a research program to connect the different signals that you can collect with the different values. And that's, I'd say, still future-looking, the sensor fusion space, and then using machine learning and artificial intelligence to connect the signals across the different spaces. And then ultimately, this is just an example of a crop growth model, but connecting then those measurements to traits in the model. Some of that can be a direct connection. We're measuring the exact same thing, and we just test and validate that these measurements are the same. And sometimes we can use more machine learning or deep learning to make the connections. So we don't actually know why this picture can predict biomass, but if we can get enough data on both sides, we can kind of use more statistical methods to go from image to picture. And then a major part, especially from the drone phenotyping work, this is a lot of work. And so we needed, and we're running hundreds of drones with hundreds of pilots globally. This is one case, and I'll bring up one case, where regulations are good. So especially in Germany, regulations came out very early, they're very clear, they're very complicated, but we could work with them. So Germany was one of the first countries to come out with laws. Unfortunately, the laws are actually at the country level and even at the state level in some cases, differences, but they were very clear and we could work with them. And then other countries followed suit, and all the regulations are pretty reasonable. There were cases with the Romanian government where we got in touch with the Air Force and we didn't want to go there, but in most cases, when we worked with the government, we got good regulations and we were able to expand. So have a global footprint, and we've trained up and really scaled, this is the benefit of scaled our phenotyping fleet. And so these are some of the traits that we're working to measure or have measured with our drone. So our major drone platform is this utilise 600. We also use the DJI Phantom 4 Pro. This is more for things like scouting or looking at field variability. If we actually want to measure things, we use the DSLR on the utilise 600. So it's kind of a beast. It's probably this big. It's hard to carry by yourself, but it has about a 30-minute battery life. But we're able, with RGB and multispectral imaging, to measure things like count plants accurately, look at early standing vigor. So this is actually differences in early vigor for soybeans, look at changes in maturity for soy maturity, measure plant height, look at disease differences, among other things. So really at scale. I'll describe a little bit more of these in next slides. So then this is just an example of the types of crops, so canola, corn, cotton, let's see, sorghum, soy, sunflower, and wheat, grown across the US and in Europe, and a little bit of an idea of kind of our seasonal aspects as well. But as I said, it took a lot to get here, it takes a lot to keep it going, but can be a valuable resource at a breeding scale. Another tool that we had, and this is something we built out over the past 15 years, is use of image analysis for maize, and then training of models to be able to count kernels accurately and in the field. And so here are some results we have comparing manual kernel counts to the computer vision models, and with our errors. So once again, another tool using computer vision for understanding how crops grow and develop and looking at differences throughout the season. And then another piece is then, based on this here imaging technology, it's also silk imaging, to be able to connect these traits once again back to the model. So some of these traits, looking at, and this is actually how the crop growth model works, is connecting one trait to the other, and that trait to another, and that trait to another through mathematical formula. So we can measure, for example, the parameters of these curve fitting, and then look at differences among genotypes. This is a case of two different genotypes differing on these numbers, and then feed that back into the model. Through computer vision solutions, we can actually connect these pieces to each other and do it at high scale. If you imagine if we had to count the number of kernels on tens of thousands of years, count the number of silks on 10,000 years, just to get a few parameters for a model, would be a very expensive proposition. I'm going to describe in a few slides so how we're connecting in with some satellite imagery. So we have a relationship and an agreement with Planet, who of course has a private satellite provider based in San Francisco. And so we get very high quality, high resolution, and high temporal coverage satellite imagery. And we get this at very, very high scale without ever having to send up our own satellites. And so one of the first things that we did, you can see this is 2015, is start looking at change detection. So this is from the 29th of July to the 31st of August to the 12th of September, and looking at the change in a field through time. So we'll see what areas are getting worse, which are the red, which areas are getting better, in blue, and which ones are not changing in yellow. So we start getting a good idea. This is more at the field level, of course, but looking at field variability, look at the impact on variability in our experiments, variability in our yield, and then can lead to better, hopefully better decision making. And once again, understanding, this is one of those maps of our yield prediction. Each one of the polygons is a very large area. We can collect data across that whole area. With some of the new satellite technologies, we can actually collect data at an experimental plot. So this is one of the plots we grew, high density, low density, different watering conditions. And you can actually see in this experiment where this is the satellite image. You can see the experiment, you can see the border, and we can then track based on the different densities and watering regimes. We can actually pull out the NDVI differences across those. So you can start actually getting down to understanding management, understanding environment through these watering regimes, and quantify those differences through satellite imaging. This is some of the scalable environment and management information you can get to then feed back into the model. A little example here on a few of our traits. So I went at kind of a high level, but ultimately, as I said, a lot of work from the pilot and analyst perspective. To fly, we collect tens of thousands of images. We have to stitch them together. We try to do that very fast and at scale. Ultimately, after stitching, we then actually have to figure out which part of the field was exactly this row. And so there's a huge amount of, as you can imagine, image analysis and kind of geospatial analysis to be able to say which part of the merged file, like this size, is that plot. Then we segment the image, we get just the plants, and then we can do count down to individual plants with very high accuracy. So this is the first trait we captured. Took a lot of work, multiple years of work to get down to the stitching and the attribution step. Recent work has been looking at plant height, so similar method in stitching images together this time. Because you have multiple view angles, you can stitch them and generate a 3D model. So you can actually look at the variation across the field. This is the output of a 3D model from our analysis, and you can see here the different plots with different border, and then actually differences across plots. And this is coming from this little section of the field where we had a small experiment, but you can see even in a large experiment, the variation you can pick up at a plot-to-plot, row-to-row level. And then we can use this for breeding decisions. And then finally, from a kind of more of a canopy health measurement, this is a plot, I think, an observation plot for northern leaf blight. And you can see very easily, you don't need very, very complicated methods to be able to quantify the differences between this, mostly the greenness across the different plots. First, we need segmentation methods to be able to pull out the leaves, and then we look at greenness, and we're more or less just trying to replace this human score. So kind of 3 different aspects of what we're trying to measure, and then ultimately replace with these measurements. And so then, in conclusion, really our goal here is to enable prediction for predictive models for breeding. So as I said, we need models that be able to take into account environmental information, management information, differences among our genetics, and then weigh how those traits and are driven by the environment so we can make environmental specific predictions. Because at present, all the decisions we make are made primarily on empirical data. We measure yield, hundreds of thousands of places, analyze it, get it down to a blob, and make decisions. Ultimately, this end-to-end prediction will allow us to simulate environments that we haven't tested in and make sure to weigh those appropriately in our decision making. A lot of this is based on investing in new field sensing technologies. That will still be important as we need to parameterize these models and understand, deeper understanding of the traits. The analytical methodologies, as I said, the CGM, the cognitive model whole genome prediction connection is key. Adding and boosting that with machine learning and deep learning analytical methodologies is also something we're working on right now. And ultimately, that will then allow to use these predictive methodologies at the grower scale. And really, once again, back to the prediction accuracy, in some cases, growers just need to know, is this field going to yield more than this field? They don't necessarily need to know how many tons per hectare it's going to be. They just need to make a decision. Should I lease this field or should I lease this field? Which field is more variable? Which field will have higher variability in yield? Some of these are actually very basic prediction outcomes that we need. And so really looking to the grower, to our clients, what do they need now? What can we provide now? And then try to provide this quickly rather than necessarily starting with hyper intense prediction accuracy from the beginning. But that's it. Thank you guys very much. I appreciate the invite.
So thank you very much for this interesting talk. We have a couple of minutes for some questions. Someone? Thank you very much. It was very stimulating. I have a question about other aspects that go maybe beyond the immediate need of the growers to make a decision for the next year. Do you also plan to include more long-term aspects, for example, soil health, building up carbon that is in the soil, crop rotation, in order to minimize pathogen pressure, to include it also into your models of predictive agriculture? Does this play a role already?
Yeah. And so those are, I guess the larger prediction framework is key. Some ways what I'm trying to focus here on is what problems can we solve today? Ultimately, I see those different, and some of those questions we need maybe separate models to ask specifically those questions. For example, questions about nitrogen runoff, you don't really need genetic differences or very complex trait-trait interactions. It can be a higher level, more basic model. Those questions are very much key, somewhat tied to regulatory requirements from the government, but nevertheless, kind of understanding how crops interact with each other, how to utilize light, nitrogen and water, how do we balance the various aspects of sustainability versus kind of grower profit, are all, and I think this commented in the last talk here, core aspects of modeling, but may need different models or may need different inputs. And so I would say right now those kind of spheres are separated. In the longer term, it starts coming together, right? So for example, what traits do we need to breed for to minimize nitrogen runoff? Or how would we breed for 2 different crops and what characteristics would they need to work best in monoculture? Some of that can come through modeling. And that's where you need all of the pieces. So it's kind of the global model needs to come together. But that is the long-term vision.
Another question?
So at the moment we are breeding rather for really, really broad adaptation in order to get a variety that is performing well in many environments basically, and in order to grant these varieties in a big market share. But with this kind of data basically, you would also have the opportunity to go back to a more regional level and develop like regional, like a land race more or less, right? I mean, do you see any leverage within Pioneer or in industry that we could go towards this situation again?
I think ideally, yes. So the challenge here is very much a business challenge, is just having a lot of different hybrids to develop, right, to produce the seed for, to grow, to hold an inventory, to sell. So that's just kind of, it's going to be a constant pull of, ideally we'd have hundreds of hybrids and they'd each be working at a very, very regional or local level, perfectly adapted for certain places. But the business need is, they'd like one hybrid to rule them all, and that's also unlikely to work. I'd see where those can come together and how kind of new technologies can help is in product placement. So we can generate the right product types and then make sure through understanding the farmer's growing condition and our germplasm and how it will fit, or the new hybrids and how it will fit, to make better matches, mostly. So rather than trying to have one hybrid that we can sell and it will do pretty well everywhere, get kind of different types and then put those really where they're going to perform, and especially importantly, do not put the others there. Do not put things there that will fail. And those are, I mean, that's a space that's coming together very quickly as well. But that's kind of where I see, hopefully new digital technologies can help solve the perennial problem. Good question.
I have a couple of minutes more for some other question.
Sorry. So I'm asking this question as a professor who is contributing to training future plant breeding students. I would like to know, what is the ratio of real plant breeders versus computer scientists, I'm not sure what else, chemists, but mostly computer scientists in your company at the moment. So what should we train for now in this new world of digital predictive plant breeding?
So it's a good question. And actually it's been one of my themes, so I think that's maybe my 6th or 7th of these seminars in this Symposium series that's been going on for, I don't know how long, 8 years. And one of the key things I've been bringing from the beginning is that breeding is a team sport, right? So when I started in 2004, I can tell you the breeders were gods in Asgard. We bowed down to them. Anything a breeder said, you listened to and you did. That has evolved. So now a breeder brings a very valuable expertise and knowledge of germplasm, of the market, connection to what the growers need and again, where the gaps are. But there's a lot of other people involved, right? Even just from a genotyping perspective, right? A modern breeder cannot make decisions without, one, decision support tools, software, all the genotyping behind the scenes work, all the plottsmanship and phenotyping work. And so that's become more and more of a team sport, and I think will become, I mean, in some ways you have a breeding SWAT team that solves a breeding problem rather than any one individual. So probably the easiest way to put it from a training perspective is to get people in multidisciplinary teams early and often. Right, so that's one of the major challenges is having people speak the same language, know how to collaborate with each other, even though they come from very different subdisciplines. And that's been something that's been actually very beneficial for me in my career. I don't have a breeding background, I actually have a evolutionary biology background. And that actually helped me because I didn't understand anything anyone was saying, so I asked the stupid questions. And I was very open to learning because I didn't know anything from the beginning. And that's something I would say, that's just continual learning, openness, collaborative work, understanding enough of computer science, analytics, software development, so that you can live in that world well. I think is what will make a modern and future breeder.
Maybe just a comment to the question here, because there was a meeting last week about remote phenotyping, and I think there was industry and academia participation. Exactly the same question came up about educating people, and I think what, at least from our point of view, the industry is looking for, because right now we have a lot of technicians which are still doing normal phenotyping, and we don't want to lose those guys, so it would be really important to have education for those people also available that can move them into the new technologies. And obviously we are really interested to have educated grad students and students in these new technologies. So I think that's very important, and I think Hans-Peter Maurer was also in that meeting, and I think he recognized the same questions, that the industry is really looking for those educated people or personnel.
Yeah, and so a lot of this, the value is really generated when, for example, you took a data scientist with no experience with breeding and a breeder. I can guarantee that either by themselves wouldn't have solved the problem. I've worked with data scientists who, if left alone, it would have been a disaster. They're answering the wrong question. Maybe they answer it perfectly, but it's the wrong question, so who cares? And the breeder who didn't have those tools by themselves to get the answer. But really bringing it together was the magic mix. And that's hard. It's hard for both sides. I've kind of raised data scientists to speak breeding and vice versa. And that's kind of, I'd say, the core people who are building.
We have time for a last question.
Tari.
Sorry.
Thank you very much. I would like to know if you have some of your digital phenotyping tools that are used to assess disease resistance rates, and how precise are the results?
So we have, the tools that we have are focused on, I guess, replacing current scoring approaches, right? So either from the ground or from the air, looking at the effect of a disease and its impact on, for example, on ears or on leaves, and quantifying that difference. So, for example, a normal scoring system, a person walks in, they look at the crop. I think this is 40% effective. 32%. This is 30%. And so, trying to replace that, and that's actually not that hard, because we're using our eyes to sense the same thing that we're being able to sense with the camera, and then all it's doing is quantifying that and classifying it. The much harder problem is picking up those effects early enough to make a decision. And that's something we're working on, but I think everyone's working on, and it's very hard. Because in some cases you're trying to determine whether the plant is going to have a disease. Because once it has a disease, it may be too late to do anything. And so that's the space in this kind of decision support or